So, okay, everyone. Can everyone hear me? Would you say yes if you can hear me? Okay, so thank you very much. So we will continue to talk about normal forms for first-order logic. So here, give me a quick reminder about where we are. So last time we talked about the basics of first-order logic. I said the first-order logic is different from propositional logic in that it allows us to talk about objects using some formal language, some formal terms, a formal thing, and then also it let us talk about properties of those objects. And for formalization of first-order logic, both in the syntax side and the semantic side, there are two things are going on. One is for the object, the other is for the properties. For the syntax side, we said there are the syntax is parameterized by something called the signature, which consists of constants, function symbols, and predicate symbols. Once signature is fixed, we have some syntactic entities called terms. They denote objects that that denotes objects. The other things that we have in first-order logic is formulas, and they denote properties of the object. For semantic side, just like we have a signature to talk about the syntax of first-order logic, we have a structure that it can be understood as meaning of a signature. So it provides what's the underlying universe of objects and how we should interpret constant, function symbol, and predicate symbols in a signature with respect to the universe. Once structure is fixed, we have an interpretation of terms, and then we also have an interpretation of formulas. An interpretation of terms, we denote it by, let me use pen. So for interpretation of term, we use things like A of t to talk about what's the meaning of term t inside the structure A, and then also for the interpretation of a formula, we use this notation A satisfies F to means that formula F is true under the structure A. Okay, and then this lecture is about the normal forms of first-order logic that allows us to transform a given first-order logic formula to something simpler. And sometimes that let me just click mouse. So sometimes that translations preserve the meaning, so that we're going to talk about so-called Prenux form and rectified Prenux form that will preserve the meaning of the formula that we started with. In other words, if we translate formula F to so-called rectified Prenux form formula F prime, they will become logically equivalent. Structure satisfies F if and only if the same structure satisfies F prime. So they mean exactly the same thing. But when you go to the Scholen form, and we are not going to preserve the meaning of a formula, instead we will only preserve the satisfiability. So if we have a formula F prime, so which is usually obtained using this Prenux form, then we will transform F prime into F double prime. They are related, but they are not equivalent, but they satisfy, they have the following property, which is that if F prime is satisfiable, if and only if F double prime is going to be satisfiable. This Scholen form is going to be much simpler than the even Prenux form and also than the usual first-order logic formula. So, and then it will allow us to design a semi-algorithm for proving satisfiability of first-order logic formulas. Okay. So we talked about a quick review, and in this big picture, we covered this elementary equivalences. So what we talked about last time is that in the first-order logic, we have all the equivalences that we talked about in the propositional logic. So all the equations, the equivalence coming from Boolean algebra, they are all going to be true for first-order logic. In addition, we have a few more formulas involving quantification. In particular, something useful for us are essentially De Morgan's law for universal and existential quantification, which talk about how these quantifiers interact with negation. And then the second part is about moving some formula inside and outside the universal and existential quantification. What it says is that if, for instance, formula G doesn't talk about any quantified variables, then we can move that formula G inside and outside of quantification, regardless of whether we have a universal quantification or G is combined by conjunction or disjunction. Okay. So that's the second property. And the third property say, it's really the third, we are not going to use the third property that much, but this is really suggesting or saying that universal and existential quantifications are generalization of conjunction and disjunction. So universal quantification can be understood as infinitary conjunction. Existential quantification can be understood as infinitary disjunction. So that's why if you have a two universally quantified formula combined by conjunction, you can essentially use one universal quantification outside. Okay, for disjunction, the same thing happens. And then the last thing talk about the order of two universal quantification and the order between two existential quantification doesn't really matter. So these are the equivalences we talked about. We're going to use these equivalences to transform given first-order logic formula into a normal form. So the first normal form that we're going to talk about today is a Prenux form. I think many of you already encountered Prenux form when you heard about logic, either in high school or in the university in a bit informal way. So the Prenux form, what it says is that it's a specific kind of first-order logic formula where all the universal and existential quantifiers are given first. And then we have a formula F, which doesn't involve any quantification at all. So it's a formula where quantifiers are taken outside. Okay, it starts with a universal and existential quantification. And then at some point, we only have a quantifier-free formula F. And this F is sometimes called the matrix of the formula. Okay. So for example, so here's a formula, and then it turns out, as I will show you, this every formula can be, for every formula F, we can find the Prenux normal form, Prenux form formula F prime, such that F and F prime are logically equivalent. So, and then furthermore, the obtaining F prime can be done in polynomial time. So there is just some transformation that goes from F to F prime, which preserves the semantics. And then the example that I'm going to show you provide how the transformation works. Suppose we have a formula of this guy, and in this formula, I think, right? The convention that we are taking in this course is that universal and existential quantification bind the tightest. So existential quantification. So here there are no confusion, but this existential quantifications bind is the kind of highest precedence among all the operators. And then what we do in this step is that we have a negation outside of this big parenthesis. Then we put negation inside this parenthesis by using De Morgan's law. So this disjunction became conjunctions. Negation goes into the first conjunct as well as the second conjunct. Now we are using this De Morgan's law for first-order logic. So this is what's written as A. So if you apply this A, then this existential is going to be changed to the universal quantification. Negation is going to put inside. Same thing happens for this existential quantification. Now, if you see this formula that you see here, the second conjunct doesn't involve variable x at all. So it doesn't have a variable x as a free variable. So we can move this guy inside this universal quantification using the rules in the first rule in the item B on the right-hand side slide. So if you do so, so then we have a universal quantification outside, and then the negation of P and the existential quantification, and then we do the same thing essentially for the existential quantification Z, because Z doesn't appear as a free variable on the first formula. So we can take it out. So if you take it out, then you get something like this, and we essentially do the same thing for the second on the other conjunct, the conjunct here, which is exist W Q of W. If you repeat exactly the same process, this exist W will be taken out, Q of W will be moved inside this the quantification. So that's the last formula that we can obtain here. So I think I have an exercise for you to do. So here's an exercise I want you to solve. So here's a formula, and transform this formula into a Prenux form using the rules that essentially the same kind of rules that I used in this example. And you can use the rules that appears in the slides on the right-hand side. I'll give you maybe 2 minutes to do this. By the way, because the quantifier has the highest precedence, the parenthesis, actually, the scope of quantification can be written. If I make a scope more explicit, it can be written like this. Okay, so let me show you the answer here. So make it smaller. Wow. What happened? Okay. Okay, so let me show you the answer. It's really simple, but I think it's good practice to do this now. So, okay, so this exercise. So we have this formula, and if I just replace implication by negation and disjunction, we have this formula. Not of for x exists y, p of x, y, z, or for x, and then there are two negation outside. Larger. Yeah, I have to move it here. And then the disjunction of r of x. So that's what we, right, that's what we have. And then if I put negation inside, this will be canceled. And then it will be replaced by conjunctions, by negation here. Also, if we move negation to inside, this will be canceled. It will be replaced by conjunction, and then we have a negation here. So if I write down the simplified formula, that's going to be for x, this is y, p of x, y, z, and conjunction of negations x, y, q, y, z, and negation of rx. So in parentheses like this, then we move this negation. So then by moving this, this will become exist x, and we put negation here. But if we put negation again, then we put negation inside. This one become disjunction, and this will disappear. Okay. So the simplifications give just 4x is y, p of x, y, z, and exist x. Now, if we put negation inside here, that's going to be 4y, negation q, yz, or r of x. So then we use the laws. So we use the laws that talk about, that allows us to move formula inside and outside of existential and universal quantification, as long as that formula doesn't contain quantified variables as a free variable. So that's the case here. So we have, so in this case, we have a r of x, and then that doesn't contain y as a free variable, so we can move r of x inside. So if you make this change, then what's going to happen is that we'll have formula like this. Right, so maybe erase a bit more. Right, so we have a formula like this. And then we do the same thing for this entire thing. So we move this entire thing to the inside of this universal and existential quantification. That's possible because we don't have a y and the x and y. So we have 4x exist y, p of x, y, z. And then we have exist x for y, negation of q, y, z, and r of x. Right. Now at this point, what we want to do is we want to move this p inside of this existential and universal quantification, but we can't really do it. That's because, I mean, the formula p contains variable x, y, and they are quantified on the right-hand side. So we're gonna soon talk about this, why this is okay. But if it turns out replacing this bound quantified variable by something fresh doesn't really change the meaning at all. In other words, replacing quantified variable by fresh new variables throughout the entire formula is gonna preserve the meaning. It will transform formula into an equivalent formula. So what we're gonna do is we will replace this exists x by x prime, this universal y by y prime. So then this y, which is bound to the universal quantification, will be replaced by y prime. X bound to this existential quantification will now bound x prime. Now after this replacement, this formula p is no longer contains any of the quantified variable on the right-hand side. So it can move to inside. So so using this fact, moving the formula, this first conjunct inside the quantified formula, we have for x exists y, exists x prime, for y prime, p of x, y, z, and negation of q of y, z, disjunction of y prime, z, r prime. Okay, so that's the outcome I mean, that's the final outcome that we can obtain by transforming this formula. Okay, so let's move to the next topic. So right, we can, as I showed, I mean, I didn't formally showed you all the justified all the steps that I used in the previous slide, well, in my solution for this exercise, but it is possible. And then understanding that is our next topic. So the key concept that will appear many times when you manipulate first order logic is a substitution. This substitution means it's an operator that take a formula and a term t and free variable x. Okay, so it's a specific kind of substitution. Sometimes people call it as a capture allowing substitution, which is different from capture avoiding substitution that some of you learned in programming language course. So this is a capture allowing substitution. And then informally, what it does is that it takes all the free variable in the formula f, I mean, for free variable x that appears in the formula f, and replace all these free occurrence of x in formula by a term t. Okay. So for instance, I mean, really, in this case, because this universal quantification bind very tightest, we have a parenthesis like this here. So this x in the second is a free variable. I mean, it's a free occurrence of a variable x. X appears here. It's a bound occurrence of a variable x. Okay, and this substitution only replaces free occurrence. So it replaces the first x by t, but it doesn't change the x appearing inside the q, but it doesn't change x appearing inside the p, because x appearing inside p is a bound occurrence. So the outcome of substitution looks like this. So now here's another exercise I want you to do. I want you to define this substitution formally using structural induction. Okay, so I will give you 2 minutes to do this. So you have to first, to solve this exercise, you have to do two things. You have to first define this substitution for terms. So if you have a term t in first order logic, which is either constant, variable, or function application, first have to define what should happen if we apply the substitution to term t. So that's what you have to define first. And the second, using these definitions, you can now define what does it mean by substituting variable x inside all the free occurrences of x inside f by term t. Okay. So by the way, because this is called capture. So it allows variable capture. So what that means is do not think too much. I mean, if you just solve this exercise naively, you will get the right answer. If you think too much, you will get the wrong answer. substitution. Okay, so let me show you how to solve this. Okay. So maybe okay. So the definition of substitution is like this. Let me get first space. Right. So we first define terms. So it's the term the definition is by induction, by structural induction. So what programming language terms you are defining in terms of recursion. So then we first define what do we mean by substituting variable x inside term t prime, and then we do case analysis. So if t prime is a constant c, in that case, substituting t, this will be equal to c. So maybe just write it like this. It's better. And then the second case is t prime is a variable y. Then we do case analysis. So this is equal to t if y and x are the same variable. Otherwise, just y. So if y and x are the same variable, we do substitution, otherwise the same, the original variable. And then the third case is if t prime is a function application. So then in this case, substitution is just defined by inductions or recursive call. So this is same as just f, where we recursively apply the substitution to each of these arguments. I mean, this is what you expect. What the substitution has to do is to find all the variable inside the term that we have, and then replace all the variable x by t. And if you follow, I mean, this is essentially an algorithm. If you follow this algorithm, that's what's going to happen. Look at all the free occurrences of x inside some term t prime, and then replace all those free occurrences by the term t. So that's what's happening here. For the formula, so now we have to define substitution for the formula. And just like before, we again do the structural induction. The first case is the formula f is true and false. In that case, I'm going to write substitution only for true. That's just like a constant case, it doesn't do anything. So we just end up with true. But the other base case is, so yeah, I'm not going to write this f equal anymore. Other base case is this predicate symbol t, so another atomic formula p applied to t1 and tn, which means that term t1 and tn are related by the predicate p, or term t1 and tn satisfy atomic predicate p. And in that case, the substitution is defined by just substituting all the terms. T1 and Tn T for x. And the other cases for propositional variable, the logical connected from propositional logic, they are essentially just by recursion. So if you have negation case, conjunction case, and disjunction case, they're all done by recursion, or in this case, induction. And so to give you one examples, if you have a formula F1 and F2, then substitution is defined by F1. So we substitute X with T for formula F1, and then we do the same thing for formula F2, and then combine the outcome together using conjunction. The last case, that's the most interesting case here. So we have a universal and existential quantification. And the cases are essentially treated the same way. So I'm gonna only talk about the first case. So if you have, let's use Y instead of X. Here. So if you have universal quantifications where we replace X by T, then we do case split. So if X is equal to Y, so then this entire formula will not contain any free occurrence of X, because all the occurrences of X inside F prime will be bound by this universal quantification. So in that case, we just ignore this substitution because there are no free occurrence. Otherwise, so we apply substitution inside F prime. Okay, so I said, to some of you who saw this notion of substitution before, I said it's a variable capture allowing substitution. That's because we are using T without any change in this universal quantification. So that's why this is called capture allowing the substitution. For instance, something strange can happen. I think it's related to some of the exercise, but suppose I have a formula like for y is equal to x, and then we substitute, we replace x by y. So all the free occurrence x is going to be replaced by y. So then according to this definition, this one will give us for y. Because y here and this x are different, we're going to follow that's the second case. So then it will become something like this. And then the result of this is for y equal y. Okay. So if you think about what happens before and after, it's a bit strange because before we are doing substitution, x and y are, this universally quantified y and this free occurrence of the variable x, they typically mean something different. In general, they mean something different. But after the substitution, they ended up with meaning the same thing. So this is not usually what people intend. And after the substitution, this x that we started with is gonna be, so that's correspond to this occurrence of y here, the y that appears on the, that you see in my pointer, is same as this y appears here, and that y got bound by this bound variable, and this is sometimes called variable capturing. And this can happen in the substitution that we are talking about, but you can define substitution in a different way where this variable capturing doesn't really happen. Because this variable capturing will happen, some result that we will have some side condition that essentially say this variable capturing doesn't really happen. Okay, anyhow, the definition of substitution that we're gonna use is this one. We have for terms, it's essentially by induction. And then for formula, it's again essentially by induction, except that for universal quantification, if quantified variable is the same as variable to be replaced, then we don't do anything, with the substitution disappears. Otherwise, it goes inside the quantified formula. Okay. Now the second result is that now for this substitution, we have the following lemma, which is called translation lemma. Okay. So then what the translation lemma say is, if we have a term t and a formula such that no free variable in t occurs bound in the formula f. So the example that I showed you, so this example doesn't really satisfy the assumption or provision of this lemma. Okay. So in the lemma, we said all the variable appearing in t are not appear as a bound variable in f. If that is the case, then we can say something about the formula before and after the substitution. We can show the relationship before and after the substitution. What they say is, for every structure A, if structure A satisfies the formula after the substitution, precisely when some modified version of the structure satisfies F. So another way to think about this translation lemma is, this substitution is a very syntactic operation which can be implemented by an algorithm. And what's written here, it's a semantic operation. We start with structure A, and structure provide the meaning for universe, constants, function symbol, predicate symbol, and variables. And for variable, we change the binding of the variable x, so that now x means, instead of x has the original value, x will have the meaning, which is the meaning of the term t under A. Okay, so we change the meaning of x. So this is an operation on the semantics. This is an operation on the syntax. And then the translation lemma say these two guys are related. And the actual benefit of this translation lemma is it allows us to avoid many case analysis when you prove some properties about the formula. So relevance lemma and translation lemmas are two key tools that we will use to reason about syntax of first order logic, the syntactic terms of the first order logic, or syntactic formulas first order logic. Okay, so here are two exercises the second exercise, actually both two exercises I want you to do. Show this translation lemma. The proof is by induction, and then if you feel like this is a piece of cake, then you can prove everything by induction, or if you don't have enough time, you just focus on inductive proof for the quantification case. And the second, this lemma, these conditions, which say no variable in t occurs bound in f. That's very important. If this condition is not true, the lemma is not true. So find a counterexample where this condition is violated and the lemma doesn't really hold. Okay, so I will give you 5 minutes to solve this exercise. Yeah, by the way, let me just mention one more thing. If you want to prove everything by structural induction, you just like before the definition of substitution, you have to have a version of translation lemma for terms. So that version of translation lemma for term looks like this for any A, for every term t prime. So it's a meaning of t prime after the substitution is identical to meaning of the term t prime before the substitution, as long as we make appropriate adjustment on the structure. Okay. It has the same form as the original. This version for the formulas, but we need something like this. So you need an induction to prove this translation lemma for terms first, and then use this fact to prove the translation lemma for formulas by induction. Okay, so let me show you the answer here. For the exercise 2, the solution for the exercise 2 is actually this guy. So we have a formula F, which is, for y is equal to x, and then substitution is replacing x by y. And then the structure A we can think about is that we have the underlying universe contain two values, 1 and 2. The equality symbol means equality. We don't have any constants. And variable, in this case, say variable x gets mapped to 1, and then variable y gets mapped to 2. Okay, so if that's the case, then this first formula say, because y is going to be bound to 2, is under A. So A is not going to satisfy. So no, let me erase this. So A is going to satisfy first this formula for y equal y. That's because for every y, I mean, equality means equality. So for every y, is equal to itself. I mean, so this is true. But the other, so that's the, I mean, that's this part of the translation lemma. But the other part is not going to be true. So the other part is, we say A, where now the something to be substituted x will now means A of t is going to be y. So that's say, I mean, this structure is the same thing as this underlying universe 1 and 2. Still equality. X now means 2. Y also means 2. Okay, so that's our structure. Under this structure, if we check whether this guy satisfies for y is equal to x, this is going to be false. It's not hold. That's because x will mean 2 here, and this formula essentially says everything is equal to 2, but that's not the case. We have a 1 and 2, and 1 is different from 2. So the point I'm making here is that here something strange happens because y, the term that we're gonna use as a replacement of x contain variable which will be bound by quantification. That's not an intended usage of substitution. So if we use this unintended use of substitution, so then this, for instance, this translation lemma will fail. Again, other things may fail, but one particular failure that we can observe is a failure of this translation lemma. Now let's go to the exercise 1, how to prove this translation lemma. And then the proof is, as I said, by induction. So if you use induction, you can show the translation lemma holds for the terms that I showed you on the right after this lemma. So for a of t prime, where x is replaced by t, same as this new updated a, I mean the meaning of t prime under this new updated meaning of a. Okay. Now we just show the, so we will use these things to handle the formula case. So I will consider only 2 cases where the first case is formula F is equal to the proposition, the atomic formula, predicate variable, and the predicate symbol applied to T1 up to Tn. And then the second one is, just like I said, the quantification. Other cases is really just almost straightforward application of the, straightforward application of induction hypothesis. So this is also the case, but let me just try this. In this case, we said A satisfies P, where, T1 up to Tn, where we replace X by T. But by the definition of substitution, this one is if this holds if and only if A, P, T1, Tx. So it holds when what I just wrote is true by the definition of substitution. But now we use the meaning of what does when structure satisfies an atomic formula P. Okay, there's a P of T something. And this is true by the semantics if the meaning of each of these guys, my pen doesn't really work very well today. So somehow my pen is not working very well. So let me. Why it's not working well? Okay, so A of T1 A of Tn Tx. If these things is belong to P, the meaning of the predicate under A, so that's by the definition of this semantics. But now we can use the translation lemma for the terms. According to the translation lemma for the terms, this is exactly the same as A, where X means A of T, and T1. In this way, same as A of T, Tn. Okay, so what I wrote there, this membership is exactly the same as A. This under new, the meaning of T1 under new A, and meaning of, all the way up to the meaning of Tn under new A belong to P of A, but P of A the same as the P of A X to A of T. So, okay, so we now, because of this equality that I just showed you, this membership say the same thing as A under X to A of T, P of T1 up to Tn is true. And that's exactly what we want to show. Okay. So then the second case is a bit more challenging. But it's not that difficult, but it requires us to use relevance lemma. So we do the replacement. So we have, say, A satisfies P of, no. So this formula, which is universal quantified formula YG, where T replace X. So we're gonna consider only the case where X is different from Y. The other case is very simple, so we won't consider this case. So if in that case, this is the same as, by the definition of substitution, Y, G, T of X. Okay, and then this means for A, so this is true for all A in the underlying universe of A. Now here we can use the induction hypothesis for this translation lemma. So we apply induction hypothesis for this guy. So then what this say is for A, but note that when we apply the induction hypothesis, our A now changed to this guy. So we have to be a bit more careful. A, Y get mapped to A and T. For A and U of A. So this is what we can write. Okay. Right. And then now we are using the assumptions of this translation lemma. The assumptions of the translation lemma is any free variable appearing in T are not going to appear as a bound variable of the formula that we are dealing with. In particular, because Y is a bound variable that will be different from any free variable in T. Okay. So this Y is not going to appear in T. And then the version of relevance lemma for terms, say this one has the same meaning as A of T. Okay. So then another thing that we know is by the assumptions, X is different from Y. So replacing binding for Y first and then X next, same as replacing binding for x first and then y next. So this gives the following equations. For A in U of A. But U of A is the same as U of A, where we replace x by A of t. So what that means is, now if you look at this entire thing as as a structure that we are using here, so then this is nothing but the semantics of universal quantifications. So we can say x A of t satisfies 4yg. And that's exactly the conclusion of the translation lemma that we want to prove. So the semantics of the A satisfy the outcome of substitution precisely when updated A satisfy something before the substitution. Okay, so that's the proof. I mean, there's some part of the proof, and actually I didn't show this. Okay, that's a part of the proof. And then the other, so what we did, where we are, we said we talk about substitutions, and we show some property of substitution, which is called translation lemma. And let's say how this syntactic substitution operator is related, can be explained in terms of some update operator on the structure, okay, which is A here. And some concept that we're gonna talk about quite a lot is this rectified, notion of rectified. It's very, very simple. It say that a formula is rectified. Essentially, all the variables have the good names, okay? No variable occurs both bound and free, and then all the quantified variables refer to different variables. So, for instance, I mean, if I have a formula like this for x, p of xy, and q of y, q of x, this is not rectified because x is used as a free variable as well as bound variable. So this is not a good example. And then another bad example is like this one. Now if I use exist x and q of xy, this is another bad example because bound variable x appears twice. I mean, so the good of a rectified formula will have something different. So instead of having x here, we will have to use something like z instead. So that's the better, I mean, this is the rectified formula. All the free variables are all different from bound variables. Bound variables are all different. So that's what rectification means. And then the proposition is for any formula. So what we want to show is that any formula can be rectified. Any formula is equivalent to a rectified formula. And then that can be proved. I mean, the key step for proving this or justifying this possibility of rectification is the proposition that I'm showing you below, which is say that if I have a quantified formula, then replacing the quantified bound variable by any fresh variable, so any variable that doesn't appear anywhere inside this formula G, okay? So that's is not going to change the meaning at all. So if I have f is a formula and y is a variable that doesn't really appear anywhere in G, it doesn't appear as a bound variable, doesn't appear as a free variable in G, then renaming this x by y is not going to change the meaning at all. Okay. So, right. So then the first thing to notice is that if we have this proposition, then we can rectify any formula. Why is that? That's because for all the quantified variables, we just pick some fresh variable which doesn't appear anywhere, and replace the first bound variable we rename by something fresh, For second variable, we also choose another fresh variable and rename that bound variable everywhere and so on. So if you keep doing it, you can do the rectification. Okay. So that's exactly correspond to what would you do if I ask you to come up with formula which is rectified and equivalent to the original formula that you are given. So the exercise one is really easy. Just rename all the bound variable one by one by a fresh variable. Okay. Now for the propositions, this proposition is easy consequence of the translation lemma. And here's an exercise, but I think it's better just to show you how this can be proved. And it's a good exercise of using translation lemma. So I think I have a proof here. So the proof goes like this, okay? So suppose we have, we have a formula. Suppose we only deal with a universally quantified formula. So A satisfies, the structure A satisfies the universally quantified formula where this X is replaced by Y. So the first line. And if we look at the original semantics of the universal quantifications, that means that for all A, if we update the structure so that quantified Y gets bound to A, what's inside the quantification is going to be true. So this is really coming from the semantics. So we can say semantic definition. So it's by definition. Okay. Now at this point, you can use a translation lemma. Translation lemma say, if you have a substitution on a term G or on a formula G, you can express its satisfaction property by some updates on the structure. Okay. So in this case, the update on the structure is we replaced meaning of the replaced variable X by meaning of this variable Y here under that structure. So meaning of the variable Y here. And this is okay because variable Y is fresh. It doesn't appear anywhere. So it meets the conditions of the translation lemma. That's what we have here. And then now, if this meaning of Y under this new structure, this is going to be same as A, because the structure say Y should mean A. And then because X and Y are different, the Y is chosen as a fresh variable, so we can, no, we don't have to do this. So it's same as A. And now the second step is because X and Y are different, we can change the order. Now, once you change the order, then we can use the relevance lemma that we talked about, which is if variable Y doesn't appear anywhere, what structure say doesn't really matter. So structure A with Y say something, satisfy G precisely when structure, this structure where Y says it maps Y something different, also satisfy G because Y doesn't appear in formula G. But this is coming from the relevance lemma. And then once after this, now we use the definition again. Then we get what we want to prove here. Okay. So the reason I'm showing this to you is because really, if you want to show this without translation lemma or relevance lemma, you can do it, but you need a very complicated structure. You complicated induction. But if we use a translation lemma or relevance lemma, you don't that allows you to avoid complicated case analysis that comes with the inductive argument. Okay, but anyhow, the important bit is that renaming quantified bound variable by something fresh, that doesn't change any meaning at all, and you can formally prove this. Okay, so now here's a more formal statements about the Prenux form, which say that every formula can be translated into a formula in the rectified Prenux form. And then the proof of the theorem is actually quite easy. So I'm gonna give you essentially, we can provide an algorithm. So we first use a De Morgan's law in first order logic to push negation inwards of the formula. So negation go all the way to the base case. Okay? And then for the second step number 2 is that we rectify the formula. So after this rectification, all the free variables and all the bound variables will be different. Then once it's rectified, then what we can do is we can use this P, because now we have essentially conjunction and disjunction of these quantified formulas. So then if we just repeatedly apply in B, then we can take all the quantification outside. And that's okay. It's possible that's because we will not have, whenever we have this kind of conjunction, because of the rectification, variable X will never appear in G as a free variable. So the rectification allows us to apply B. So if you keep applying B, we can transform any formula into a Prenux form. Okay. So here's the one exercise I want you to do. So apply this transformation to only the first formula. Okay, I have a 2 exercise, but I'll give you 1 minute and then solve the first exercise. Okay, so let me show you the answer here. So then we just follow this algorithm in the proof. Then so the algorithm say first push the negation all the way inwards. So then if you do so, the outcome is going to be for X, negation of P, XY, and conjunction of exist Y, negation of QY, and conjunction of exist X, Q of X. And then we do the rectification. We have a free variable Y, which we can't really rename it, but for other bound variable we can rename. So for Y, we replace by Y prime. For X, we replace by X prime. Once you do this, then essentially what boils down to is you just take all the quantification outside, because that's what the rule B tells us. So if you take all the quantification outside, while making sure that you are not really changing the order between existential and universal quantification. So in this case, essentially the quantifiers are not nested at all. So if you take all of them outside in any order, you have a Y prime, X prime, CS negation of P, XY, and Q, Y prime, and then Q, X prime. So this is the form, the rectified Prenux form that we can obtain by essentially the algorithm inside the proof of this theorem. Okay, so now the really important concept that maybe we have about 5 minutes. I'm gonna talk a bit about this important concept and say complete this discussion maybe on Wednesday. Really important concept is a Scholen form. The formula is in Scholen form. For a formula to be in Scholen form, it should first be in a rectified Prenux form. So it should be of the form where we have a bunch of quantification, x1, xn, and some formula f. And then all the bound variable and all the free variable should be different. Okay, so it should be a rectified Prenux form. But one big requirement is that it shouldn't contain any existential quantification. So, which means that all the quantifier there should be a universal quantification. So that's a very specific form. It's to say, I have a formula where all the quantifications are the outside, and those quantifications are all universal quantification. And this is Skolem formula, Skolem form. I mean, here are two exercises I want you to do when, I mean, maybe not now, but especially the first exercise, think about this. For the answer for the first exercise is no. So because I mean, you can kind of argue informally that, you know, if you just use a universal quantification, obviously you can't really express all the properties of the first order logic formula. I mean, existential quantification are really important. It's add something new. So just using universal, you can't really express all the first order logic formula. That's a kind of very informal argument, but the exercise one really, the proper solution for exercise one is to come up with the actual formula, which cannot be expressed, it cannot be equivalent to a formula in a Skolem form. For exercise two, I mean, actually the solution for the exercise two is this proposition called the Skolemization. Then let me just first explain the idea of the Skolemizations, and then for the proof, we're gonna look at it maybe the next time. Well, maybe I'll give you a bit of the idea of the proof. Then we will continue and finish off this Skolemization. And homeworks involve Skolemization, so having some understanding about this will help you to solve the homework. So the Skolemization is that, so we wanted to transform a formula into a formula in Skolem form. But as this exercise one suggests, we can't really always do it with preserving the meaning. So instead, we lower the aim, and our aim is if we have a formula f, which is in the rectified Prenux form, and we want to come up with a formula f prime, such that although their meanings may be different, we want that they will be equi-satisfiable. So if it's satisfiable, we don't know it's satisfiable or not, but if it's satisfiable, if and only if f prime is satisfiable. So it's a satisfiability preserving transformation. Now the question becomes, how can you do this? Now, to change any formula in Prenux form to the Skolem formula, one thing we have to do is we have to get rid of existential quantification. Okay, so now this proposition tells us what should we do to get rid of existential quantification. It says that if I have a formula f, which has a bunch of universal quantification followed by existential quantification, okay, so this G doesn't have to be quantifier-free formula. It may have universal and existential quantification. It can be anything. And Skolemization tells us that now, if you pick some function symbol f, which take RTN, but this function symbol is fresh. It's not appearing in the formula f at all. It's just some fresh function symbol. And now, if we replace this variable z inside, variable z inside formula g by this term f applied to y1 and yn. Okay, so we will have a new formula f prime. Okay, so far we are just describing an algorithm. We pick fresh function symbol f of RTN, and we replace z by this function f applied to y1 up to yn inside the formula g. So we obtain f prime. And the kind of punchline of this proposition is formula f and f prime are equi-satisfiable. Okay? So formula f is satisfiable if and only if this f prime is satisfiable. Now, these two exercises ask you to prove, and then the first use this proposition to come up with an algorithm that take formula in Prenux form and produce formula in the Skolem form. And then second, it asks you to solve this, prove this proposition. So we're gonna go through it a bit more carefully next time, but let me just give you some idea about how the proof goes so that you can think about it and maybe use this idea to solve the homework exercise. The idea is that if, so in some sense, this formula f for all and that exist, if we have a satisfying some structure that satisfies this formula f, that tells us how should we build this function f, this function small f. Okay, so if we have some a which satisfies formula f, which is y1, yn exists z and g, then that tells us how to build this small f. So it tells us how to build this semantics of f. And how does it work? The idea is that, I mean, if we follow the interpretation or semantics of this universal and existential quantification, it's a, for all elements, for all binding of y1 to an element in underlying universe of A, y2 to an element in underlying universe of A, and so on, there should exist some element in the underlying universe such that blah. Okay, so you will have a binding of y1 to A1 in which binding can be anything in underlying universe of A, binding of yn, an to underlying universe of A. These interpretations, this satisfaction relationship tell us we should be able to find some A underlying universe binding for Z in underlying universe of A, such that some good thing happens. Now, this binding, this A can actually be used as a map outcome of applying this function f to A1 up to AN. So this is what we define this. So we define function f such a way that if we apply function f to A1 in this structure A, A1 up to AN, then that outcome has to be equal to A, and which A is going to be determined by these interpretations. If you do so, then you can show this, the new interpretation of this function with the function symbol, then this formula f prime is also going to be true. And also show that the other direction, if f prime is satisfiable, then showing f is also satisfiable is not, that direction is actually quite easy. Okay, so we're gonna prove this in the next time. And yeah, so that's it for today, and I hope to see you on Wednesday.